steps. So after selecting Kratos, you have several possibilities. Well, this is not all the things that Kratos can do, but these are the possibilities that have the Kratos interface for users. So you select structural analysis. We could have changed it. We have only this now. And you have to click next. Only clicking this button is not going to do anything. So click next. Then you have to select the spatial dimension. So here there is dimension with S and here with T. We have to correct this. You select the dimension. After that, it says what structural type do you want to simulate. So you can choose in the solid mechanics application between beams, shells, membranes, solids, and generic. Okay, these four types are independent. The generic is because if you want to combine some of these structural types. The thing is that we have to be careful because you have to know which are the degrees of freedom, which are the typologies of a structure that we are combining, because maybe they are not compatible, right? So when you select this initial thing, the Kratos problem title starts, and the menu just appears in this part of the Gits menu. Also, you have some menu here in Kratos, but well, the things that you have to manage is this. We can see here that there is a groups icon. With the groups icon appears just a window with a window like layers. Then we have these two icons here. One is defining the model properties. The first one is one here, sorry, and the other one is for defining the materials, right? We'll see the icon for defining the model properties just opens this window, right? When you have here the model and the materials. With the structural simulation, the things that we have done with the wizard is just selecting the things for the structural simulation that we have already selected. So when it opens these menus, we can see a little bit. It says structural simulation, it says analysis type, right? Solution and strategy, properties, it means the properties of the materials that we are going to use, elements, loads, boundary conditions, and finally some menus for the results, for seeing the results. The thing is that, well, this is the general structure for a finite element program, right? We have to select which elements we are going to use, which loads we are going to apply, which boundary conditions we are going to use, and here the solution strategy, well, means something about if we want to do a static analysis, dynamic analysis, and which type of algorithms we are going to use for this strategy. So we start with the most simple example, and the most simple example is to use in the analysis type of small displacements. Small displacements are large displacements are evaluable. The solution type that we have selected is a static, can be a static and dynamic, also quasi-static, and also there is another type for membranes that is well, a type of dynamic thing. So solution type we selected a static and analysis type linear, right? With analysis type we are going to control which is the solution solver that we are going to use. If we select linear, automatically we have here the linear solver. If we select non-linear, we will have here just iterative solver with different type of menus to select which are the conversions for non-linear solver, which type of non-linear solver we want to use. If we are selecting instead of static dynamics, then we can select if you want it implicit or explicit, right? And if we select dynamics, we will see later appears just another line here about that allows you to select which is the time step that you want to use and which is the total time of the simulation. So first thing in the finite element program, create the geometry. I think in the USB or in the documentation you have already a geometry created. So if you want to import from Git without having any problems, you can just import and go to insert Git model because it was created with Git. And well, this is only not to write the geometry here in Git. We have already written it. So we have this geometry. This is a 3D geometry. It has to accomplish with the things that we have already decided that have to be a 3D problem. And once we have the geometry, we start with selecting the data that we are going to use. So the first thing is selecting the properties of the material. In this case, we go to the properties, we click here, and this menu is open. The first thing is the property ID. We can change the name if you want. The second thing.
Exactly. What is actually the name of the file you have just shown?
Yes, I have not said the name. I think it's called Kratos. I don't know exactly. I think it's the folder. I can show you. Yeah.
The K22 session.
Is this one?
Solid
Solid mechanics, and then this one is on.
This one, Kratos example rod 3D. This one. Yes. So we can select this thing, and I don't know, put the roll back now. Yes. 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 No sé, volver al siguiente.
una mica.
This is also working. Did you find the file?
Yes.
Yes. So we have to open again. Let's open again. No, not this one. Okay, so we can. Good. I think that we can open it again. File's open, but well, we can also do that. Import insert with model, and we get only the geometry, and we can start from this geometry.
Maybe you can open the key.
Yes. Well, I need where do you have it here?
Okay.
Is this one? No.
No, the 12 one.
This one. Okay, maybe I have explained it too fast. If it opens, we can do it manually. The computer is faster. Good. So I start from the beginning. So the first thing I have done is just going here. It's difficult. Kratos, spectral analysis. Next, 3D. I have selected solid. Next. And now the Kratos Plot time is opened and the menus appeared here, right? I have opened this, I have explained it a little bit, which are the different type of things that we can choose. So let's import the model. Insert with model. Maybe I can do not in C. No. The thing is that I need to know D. This is my one? No. Yes. This one. Open. Good. No, this is the problem of this computer, right?
This is the part you can check.
Yes. Did you have you done this with your computers? Is it working? Yes. Well, so I think it's better to continue with the presentation, not using it, because we can have these small technical problems. So I continue with that, right? So okay, we have opened this, right? What we can see here in the model? Several lines. After we have defined the lines, we can define the surfaces, and the surfaces are these things that are just depicted in rows. And inside of these surfaces, that is the cover, we have the volume depicted in blue, right? So this is a 3D model. We can render it. If we go to view, render, and we see a nice figure. Good. So we have the geometry and we start with the problem. First things, the materials, right? We need to define material for this piece, for this connecting rod. So properties, we open the properties, we select which type of structure we are going to calculate. So here we have in the property that beams, shells, membranes, and solids are the same ones that we could select at the initial introduction of the problem. So we select solids. We also select which is our constitutive law. We have 3 different constitutive laws: elastic, isotropic, hyperelastic, isotropic, and plastic. Hyperelastic, plastic. And after that we can select the material, right? We have these 3, we can create our materials. If we go to, instead of the model window, to the materials model, we have here different materials and we can create new ones. In the next tutorials, somebody will explain you how to create new materials. But, well, we are going to select this one. We can select this one and change, for example, the ion modulus on the point or the Poisson ratio, if we want. So, or we can just add a new material and put the new properties. Because this is elastic model, we need only these 2 coefficients, the elastic modulus and the Poisson ratio, and this is enough. Once we have selected all these things, we just press OK, and we have the material created, and the material appears here. Right? We can change after that if we want to create, instead of this elastic isotropic one hyperelastic material, we can change it here. Well, once we have created the properties, and this is the order, because to create a new element we need the properties already created. So we are going to select the elements. We just click on the elements. Now we have only solid elements here, because the menu is just opens the windows that we have already selected. So we have solid elements. We can choose which is the element type that we want to use, usually 3D tetrahedra and hexahedra. And the property that we are going to assign to these elements. That is the property 1 that we have already created, right? So the next thing is to say, well, which is the volume that we want to measure with this type of elements? We have 2 options here. The first one is, let's assign the element to volume. We are in 3D, right? And let's create just the group to assign this element. So we push on this icon, and we select the group. And this is the thing that I have done in this example, right? So we just push it here, and I selected the volume where I wanted to implement this tetrahedra with these properties, right? There is another possibility, is to have initially a group created, and we can select here, just opening this window, and we can select a group that contains this volume, right? In this tutorial, we are going to create all the groups automatically, right? So I create the group, I select the volume, and the group is created with this name, solid element, 0, right? And after that, I press OK, and the new elements are selected to this group, and it appears here. This solid element group appears in the groups window, right, when it is created automatically. As I said before, we can create these groups initially and then assign directly the elements condition to the group that we have already created. So next step. Now we know that we are going to mesh with solids, to make the mesh with tetrahedra. Let's apply the loads. The most simple one, self-weight. Right? I apply the self-weight. I have to be careful. I have to look at the axis of my model, right, and put the self-weight in the correct direction. Good. For me, I have seen that this model is, well, it's brighter in a special direction, so I wanted to depict that the gravity is going with the direction of x, right? So, well, negative x. I think this is depicted. So, for me, it will go to this direction. I have it rotated, I don't know why. But it will go to the x negative, so it will go to this direction, right? I think this was just rotated. So I put the direction here of the gravity, and this is the value of the gravity, 9.8, right? I have to select also in which place I want to apply this load. So in this case, I will select the same volume where the elements were selected. So I just push on this button and I select the solid in element 0. So all the volume will have the load of self-weight applied. Right? You will see that it's very simple to apply the load like this. Next step, I will not apply any other load. We can apply self-weight, we can apply punctual loads. This can be applied in a point, in a line, or in a surface. Moment loads, this is in the case of shells, right? Or pressure loads, also to apply to in a surface or in a line. Right? The pressure loads are follower loads, and the other ones are not follower loads. So, next thing, boundary conditions. I'm only explaining you the more simple example, right? Boundary conditions, we are going to fix the displacement, so where in the figure? This is static analysis, we need to fix on, right? So I'm going to fix these two surfaces of my model. These are the inside surfaces of the rod. I select displacements. When I select displacements, I can put here the value of the displacements. Pushing the fixed tab, I will see if I want to just fix X, Y, and Z, or only one of them. In this case, I want to fix it all. And I do exactly the same. I create a new group and I select these two surfaces, this one and this one. Right? Automatically it creates a group, name it this one. It appears here in the window of groups, and I push finish, I push OK, and then it appears here, displacement values and what is fixed. I can change it after that. And if I make a mistake, I want to say no, I want to fix only X and Y direction and set it to be free. It can be done. Okay? So we have done go back. Eh? I have done the elements, we have assigned the elements, the loads, and the boundary conditions. Everything is assigned. We can just mesh and compute, right? But the thing is that we need first to set the results. What do we want as output? The first thing is the output delta time. This is a static analysis, so one result will be brightened. But if we have a quasi-static analysis or dynamic analysis, we need to know how many results we want to write it. So this is a time, so we'll have to look at our time step and put a time that have to be current with the steady state, right? Then we can select the results on nodes, displacements, accelerations, velocities, reactions. Here, loads, if we want to repeat the loads. Then we can select which results we want to print on the Gauss points and the integration points. Right? We have this for default is no, so I have set it yes, yes, and yes. Well, this is also. And the last part of the results are the options, different options. Which are the options? The result format, binary. Binary, just the files that are going to be brightened will occupy just small memory, but we are not going to be able to open it and to see what results are in this file. So we can select binary or ASCII. In ASCII, we are going to be able to open the files. If we want to write the deformed mesh or the initial mesh, if we want to write the conditions, for example, for us will be these ones, the displacements. So we get 2 extra boundary surfaces with these conditions. If we want to write the particles, it means all the nodes of the mesh in this case. And if we want to write it with a single file or a different file. So we have a quasi-static or dynamic analysis where we will want to write different results. We can choose all in one file or each result in a file. So in this case, I have selected a single file. And well, next step, mesh generation. The mesh is generated by Git, so Kratos is not going to do nothing here. So we go to the mesh window, generate a mesh, and we select the size. We can, well, there are different options. Select the, if we want to structure it, well, all the options that Git offers, right? So after generating the mesh, we have this initial model. We get, for example, this mesh. We have to see if the mesh is good enough. Maybe here we need some more elements, depending on on the type of response, deformation response. So after that, when we have the mesh, we run the simulation. To run the simulation, we can press this button, right? And this is enough. We press this button and we just wait to get a window with the result. There is two options. Get a window that says the computation is performed successfully, right? This is the one that we desire, something like this. Have finished it. We are going. It can be another type of response of this. Occurred some error, and appears error. So if something occurs and there is an error, we have to look if we have assigned correctly the boundary conditions, the loads, right? Or if there is another thing. Usually there is some message about what happened, right? If the simulation is large and we want to know what is doing the computer, we can just push this icon here, right? That is the process information. So a window is opened and we can see what are the steps that the computer is following. If some error occurs, we have some possibilities. Here I have opened the folder of the example of Git that we are running, right? If everything is correctly assigned, the things that we can see in this folder, or the 4 files that are important are the first one file that have the name of the example, structural analysis.ndpa, right? This file contains the properties, the nodes, the elements, and the conditions. So you can open this file, and it's an ASCII file, and we can see that there is the mesh, and it's correctly brightened. So we can make this check if something is wrong, right? Another 3 files that are important. The materials. The constitutive flow that we have selected will be brightened in this file that is called materials.pi, right? So the constitutive flow, and we will have extra properties, for example in a bin, we need to write the inertias, the cross area, some other properties. We can find these properties here in the materials. And the next file that also is important is the project parameters file. All the things that are not the properties, the elements, all the things that takes into account if the analysis is static, which solver we are going to use, right? Which has the output results. All these things are written in the project parameters, right? So if we want, we can check this if something is wrong there. Because finally, the run of the program, or the bat file that is going to run the program, are going to just to execute this file, trackers structural p2pi, right? And this file, that is a Python file, is going to ask for the parameters, ask for the materials, right? And is going to read also this one. So usually if we get an error, it's possible that says that something is wrong inside of this file. It's because maybe we have just something here or here is incorrectly written, right? So this is not a user thing, but it's good when we get errors, we can check if these files are in this folder and if these files are correct, right? Good. So for us, the answer was that. Everything is correct, and we can go to the post-process, right? If we go to the post-process, well, we can go to view results. There are several options to see the results, to view the results. So, for example, we choose displacement, and we get a displacement. Now we can put, now the axes are correct here, right? The gravity was minus x. So we get a displacement. Remember that we have fixed 2 surfaces here. And we also get the stresses. In this case, Cauchy stress. The S means the sigma, right? The sigma. Usually it's written by an S here. And also, for example, just comparison with variable indices. Let's do an extra thing. Let's go back, and instead of doing a static analysis, let's do a dynamic analysis. So we can go back to the pre-process. This button goes from the pre-process to the pre-process. So now we go to the analysis tab, and instead of selecting a static, we're going to select dynamic, right? The next thing that we are going to select is time integration implicit. I said that it can be explicit, but we select implicit. And now we have the time parameters window here up. We can select random step and the total time of analysis. This is related with output results. Maybe we have to see, well, if my time step is 0.1, let's write my data results 0.1, or in this case, every 2 results 0.2. Good. And now I have activated to write the velocities and the accelerations also, because it's a dynamic analysis. Just changing this, I run the simulation again, have computed correctly, I go to the post process, and now I'm able to see the accelerations of this and the velocities, right? And we also can animate the results, right? And I don't know if it's going to run, right? No be able. ¿Puedes pulsar escape? No, that's great. Well, it's a small displacement, so it's not going to move a lot. I think there's a deformation multiplied by this factor that I'll just be breaking, right? Just be breaking. So, well, there are several possibilities. This is the more simple case that we can analyze, static thing, 3D. And, well, thank you for your attention, right? Next one. I haven't said, did you have any question about that? Did you have any question? Yes?
No, era el fluido.
No, es que decía que la había abierto por equivocación los de Free Surface, creo.
Sí, no, pero ¿dónde están los switches? Que no me
Si internet tingués temps, després del cafè. No sé si
Bueno, pots.
Sí, no, és un problema el Puyer, no val la pena.
Per tot i aquest no, m'atrau com funciona, no sé passar d'una finestra a una altra. Sí, intentaré hacerlo aquí, de todas formas. Lo tengo aquí. Lo pruebo desde...
¿Desde aquí?
Sí, ¿no?
No hagas import.
No, yo tengo, la geometría es fácil. No, yo lo dibujo.
Ah, vale.
Es un cilindro.
Bueno, si lo tienes, ábrelo y ya está.
Bueno, sí voy rápido, venga. Aquí tots posant la mà a la caixa, home. Esa mano, que luego va al pan.
Assistència tècnica, és com el Sant Bernardinos de Suïssa que van a la polleta de...
Sant Bernardinos.
Crec que això no tenia cap.
Bueno, me pongo aquí porque... Sí, pero si tengo que entrar... Ah, bueno, claro. Okay, so while I'm Jordi Cotella, for the next few minutes I will try to introduce you a bit to the fluid dynamics problem type and the capabilities that we have available.